Hi, this lesson is about the derivatives of logarithms, logarithmic differentiation, and inverse trigonometric functions. The video will be split up into two parts. First part will focus on logarithms and their derivatives. We'll do logarithmic differentiation and inverse trigonometric functions in part two. So first let's do a reminder about what logarithmic functions are. And logarithmic functions and exponential functions have a relationship. So every logarithm can be rewritten as an exponential function and vice versa. So for example, if you say y is equal to log base b of x, then you can write that as x is equal to b to the y. In both cases, the b is considered the base. When our base is e, that's what we call a natural logarithm, and we use the notation ln to indicate a natural logarithm instead of log. So if y is equal to ln of x, then rewriting it as an exponential would mean that x is equal to e to the y. So there are logarithmic laws or properties that are helpful when you're taking derivatives. It actually oftentimes will make things very simple. So remember, the laws are that if you have the log base b of x to the n, that can get rewritten as n log base b of x, and these two would be equivalent. This is not a derivative. These are logarithmic laws that are learned in pre-calculus. And so we'll be applying these laws before taking the derivative in some cases. The second law is regarding products. So the log base b of x times y can be rewritten as the log base b of x plus the log base b of y. And the third one is a quotient law, and that says that the log base b of x divided by y is equivalent to the log base b of x minus the log base b of y. So when your logarithms are rewritten the way they are on the right side, that is called expanding the logarithm. So there's a few things we should remember about natural logs and e, and that is that the natural log of 1 is equal to 0. So the point 1, 0 is an x-intercept on the graph of natural log. ln of e is equal to 1. So on the graph, that would be the point e comma 1. And e to the ln of x, because e and ln are inverse functions, that's just equal to x. So whatever x is, if it was e to the ln of 3, then your answer would just be 3. Okay, so let's practice using these laws to expand a logarithm. So here, something got erased. So we have the natural log of 5 root x divided by y cubed. First thing I did was I rewrote the radical as 5x to the 1/2 divided by y cubed. So I'm going to be using all three of these laws because I see that I have exponents associated with the x and the y. I have a product in the numerator, and I have a quotient overall. So when I expand this, I rewrite the product in the numerator as the sum of natural log of 5 plus the natural log of x to the 1/2. And then the quotient, we write it as a difference, so that'll be minus ln of y. But then we can refer back to the first law, which says when you have an exponent, that exponent becomes a coefficient. So your final expansion is ln of 5 plus 1/2 ln of x minus 3 ln of y. Here's another example of where we will expand and simplify as much as possible. I have the natural log of e to the third divided by x. So here I'm going to use the first and third law. The first one because I have an exponent, and the third law for quotients because I am dividing e cubed divided by x. So I rewrite the ln of e cubed over x as ln of e cubed minus ln of x. Then I put that exponent in front of the ln on the next line. So I have 3 ln of e minus ln of x. But remember, ln of e is just equal to 1. So you can simplify. And so your final answer is 3 minus ln of x. Okay, so now let's talk about derivatives for logarithms and exponential functions. So these are new rules. The main one you should be concerned about is this one. It says that the derivative of the natural log of x is equal to 1 over x. Now the other two, although also used, they're not as frequently used. The second one is regarding a log of any other base other than ln, which is just very straightforward here. If you have log base b of x, there is a change of base formula which allows you to write that logarithm of base b in terms of this ratio, which is ln of x over ln of b. But ln of b is just a number, so you can write that basically it's a coefficient of ln of x. 1 over ln of b is the coefficient of ln of x. So when you take the derivative of that, you will basically be multiplying 1 over ln of b times the derivative of ln of x, so you get 1 over x ln of b. And the last one says that if you're taking the derivative of b to the x, that is equal to b to the x times ln of b, as long as your base is greater than 0. I'm actually going to show you another way to find derivatives of exponential functions like this using logarithmic differentiation. But it is very straightforward when you have something basic, like if you say y is equal to 2 to the x, then your y prime will be 2 to the x ln of 2. Okay, so if you're applying this formula directly. Okay, so if possible, you want to first use the laws of logarithms to expand the logarithm and then take the derivative. But that's not always a requirement. Sometimes that doesn't make any sense at all. It's not something you'd be able to expand, or it's just as simple without expanding. So in this first example, you don't need to really expand ln of 7x, although it is a product, 7 times 2 is a product. You can take the derivative by using chain rule, where your outer function is your ln and your inner function is 7x. So with chain rule, you take the derivative of the outer function first. So I'm using this. It'll be 1 over 7x times the derivative of the inside, which is 7, but the 7's cancel, and so you're left with a derivative value of 1 over x, which looks exactly like what that was when it was just ln of x. So whenever you have a coefficient in front of the x and you're taking the natural log, you're really going to get the same result. You're just going to get 1 over x. But in the next example, it's a little bit more complex. So you can apply chain rule again, but chain rule would be a little bit more complicated because my outer function would be ln, but then my inner function would be a product of two functions, so I'd have to use product rule. So I'm going to show you another way to do it by using the logarithmic laws, which actually makes the derivative very, very easy. So the first thing I did here was I expanded ln of e to the x3x into the sum of three terms. The product of e to the x times 3 times x becomes a sum. So that's ln of e to the x plus ln of 3 plus ln of x. Now, ln of e to the x is just equal to x. So if I simplify before I take the derivative, it makes things even easier. So I really just have to take the derivative of x plus ln of 3 plus ln of x. But the derivative of x is 1. The derivative of ln of 3 is 0 because that is a constant. And the derivative of ln of x, well, we just talked about that. The derivative of ln of x is 1 over x. So that is my second term. So the derivative is 1 plus 1 over x. Okay, so here's another example where expanding the logarithm first is more convenient than taking the derivative as it is. Again, if I took the derivative as it is, I would have to use chain rule first, where ln is the first function, square root is the middle function, and my innermost function is this quotient. So once I get to the point of taking the derivative of the innermost function, I would have to use quotient rule. So that can get very busy in terms of the algebra that needs to be done. So instead, I'm going to expand it. So first thing I did was I rewrote the radical as the expression raised to the 1/2 power. So it's the natural log of t plus 1 over t minus 1 raised to the 1/2 power. Then I use my logarithmic laws. Notice that this is both still y. I haven't taken the derivative. The 1/2 goes in front, and then you can rewrite that quotient as the difference of two logarithms. Now I'm ready to take the derivative. That's as far as you can take it. You cannot distribute ln across. So this is not equal to ln of t plus ln of 1. So if you have that habit, please break it immediately. That is not true. So, but I can apply the derivative, and in this case, I still have to apply chain rule, but it's a very simple chain where ln is the outer function, t plus 1 is the inner function. So I take the derivative on the next line. So the derivative of the natural log will be 1 over t plus 1 times the derivative of the inside, but the inside is just 1. So you can write times 1, but it doesn't really change much for you. And the same thing happens with the second logarithm. It's 1 over t minus 1 times the derivative of the inside, which is again just 1. And then on the next line, I got a common denominator, which is t plus 1 and t minus 1. So the first one gets multiplied by t minus 1. The second one gets multiplied by t plus 1. And now you have your like terms in the numerator with a common denominator in the denominator. And when you distribute your negative and combine like terms, the t's will cancel, and -1, and this becomes a -1, gives you a -2 in the numerator. But these 2's cancel, so your derivative is -1 over t plus 1 times t minus 1. Okay, so here we're going to find the instantaneous rate of change at x equal to 6 for y equal to the natural log of 3x squared. Remember, this is just another way of being asked to find the derivative. And once we find the derivative, we will plug in 6. So here, again, I do have the option of expanding and then taking the derivative, but this one is pretty straightforward. I'm just going to use chain rule. Things cancel very quickly. So when I apply chain rule, I get 1 over 3x squared times the derivative of the inside, which is 6x. The 6x and the 3x squared simplify, which leaves you with just y prime equal to 2 over x. But then when you plug in x equal to 6 as requested, you'll get 2 6, which means your instantaneous rate of change is 1/3. So that's it for this lesson. Give the homework a try. Good luck.